So as Guido mentioned, my name is Steve Miller. I work at the MathWorks. A large portion of the conference that we've heard so far has been about the controller side, and in this presentation we're going to talk about mainly the plant side, or the physical system. This presentation is going to be about vehicle models, specifically vehicle models that encompass the entire vehicle at the right level of detail, modeling methods that make it easier for engineers to model the system, and vehicle models that cover the entire range of the development process. So let me set the stage for you for this presentation. In the group that develops the vehicle, I am the engineer that is responsible for developing the transmission. I create the models that are used to determine the architecture for the transmission, decide which technologies will be used, and to develop the control system. To develop that and to test the performance of the transmission, I need additional models. I need to have models of the environment, the remainder of the vehicle, driver models similar to other presentations we've heard today, and the conditions under which vehicle performance will be tested. So I have the challenge to decide, am I going to develop these models myself, or will I obtain them from someone else? Other engineers working on the vehicle have access to tuned driver models, have the experiments set up that will be used to assess vehicle performance, but for some vehicle level decisions, a more detailed model of the transmission is necessary. For us to work together efficiently, ideally these models would all be in the same environment. So that is where our story begins. The agenda for our presentation is as follows. First, we're going to talk about the needs that engineers have in developing these systems. We're then going to present two portions of a solution that meet these engineers' needs. And finally, we'll show you how to combine these two products to deliver the required capabilities. The first need that we're going to highlight has to do with the methods that are used to model the physical system. Many engineers rely on signal-based methods or input-output methods to build up a model of the system. These methods are very attractive because they have complete flexibility. If you can express the output of your model in terms of the inputs, you can create the model. However, this method comes with its share of difficulties. Let's say that the transmission that I'm modeling looks like this. And if I were to create that model using an input-output method, the model could look like this. You can recognize the structure of the system. But for me to create this model, I need to have expertise in a number of different areas. I need to understand physics so that I know which effects are important and which ones I can neglect. I have to have a strong mathematics background so that I can express those effects in terms of equations. And I need a programming background so that I'm able to implement that in the tool. Let's say a new technology is introduced. I then have to model that component and integrate it into the overall system model, which may mean rederiving and reprogramming those equations. That is an error-prone process that can take time and lead to mistakes. Let's say, for example, that the transmission continues to increase in complexity. You can see that incorporating this into the system-level model will involve further changes to the overall system equations, and the model is resembling the structure of the original system less and less, which makes it more difficult to read, to explain to others, and to maintain. To address these challenges, a better method to use are physical modeling methods. In physical modeling methods, instead of using inputs and outputs for the components, they are connected with physical conserving ports. So the connections that you see in this model represent physical connections. By doing this, it makes it easier for me to build an accurate model more easily. The system-level equations are derived automatically, so I don't have to rederive and reprogram the equations for the entire system as the complexity of the transmission increases. The model is much easier to read. Looking at this example, you can see what the structure of the system is, which components are connected to which other ones, and in which way. And finally, it's easier to update this model. As new technologies become available, such as new batteries or new control systems, these are easier to integrate into a model that has these types of connections. The next need that we're going to talk about are the need for ready-to-use simulation models, and Hagen will address this topic.
Yeah, thank you. Steve has introduced this very powerful method to solve problems in simulation or in modeling of plant models, but in addition, ready-to-use simulation environment is necessary, especially if when you are a controller developer, because if you develop your controller in a model-based design area, for each test, for each simulation, you need the counterpart of this controller functionality. You need the plant model, and as a controller developer, you want to focus on the controller functionality, and you want to spend as less effort as possible to the plant model. And that's why a ready-to-use simulation environment for plant models could be very helpful. And normally, if you test a controller, you need more than the plant model itself. You need also a kind of simulation, environment simulation. This can be the vehicle, this can be a driver model for driving maneuvers, for driving cycles. This could be a road model also, or a dyno test bench. But the model itself is only one part. The work with the model, the usability with the model strongly depends on the parameter handling and on the handling of the simulation results. And so a model environment should give you a very easy to use access to these things. And because of a general model environment or a ready-to-use model environment is a kind of general, it should be possible to integrate specific models for specific tasks. And of course, all these things are necessary for all the development cycles, for all the steps in the development cycle. And it would be good if you could use the simulation environment in all these steps, from the offline simulation, maybe in MATLAB Simulink, to the HRL testing at the end of the development cycle. But for the HRL testing, we have additional specific requirements, and let me shortly explain these. In a vehicle, the ECUs are connected via bus systems, and each ECU communicates with its plant with sensors and actuators. And if you describe this in an HRL simulation scenario, you need specific models for each specific plant, and in addition you need the connection from the models to the ECUs. And so we come to an additional very strong requirement, which is real-time capability. And of course, all these complex models from different domains, brake hydraulics models or thermodynamics models in the engine area or mechanical models have to be connected together. And in addition, the real-time calculation capability is not limited to the model itself. It has also to calculate the communication, the sensor and actuator communication, and also the bus communication. And in the real-time domain, it is you have to ensure, in addition, that the real-time that the model is stable in real time, and so you need to implement different solver techniques for different domains, which is very important. And of course, the model can handle the state-of-the-art real-time processor hardware, which is normally a multi-core processor system. It should handle this. Yeah, what will you see in the next couple of minutes? We want to introduce two systems in this area. We want to show you the physical modeling method from MathWorks and the ready-to-use simulation models, the automotive simulation models from dSPACE. And finally, we want to combine them and want to show you how to simulate a complex model within a ready-to-use simulation environment.
So hopefully you understand the needs of what engineers have to develop these systems. Now we're going to talk about the two portions of the solution. So Sim Driveline can be used to model the rotational mechanical portions of the system. It's an extension of Simscape for modeling these types of systems. It's tightly integrated within Simulink and has been available for a number of years. It is optimized for efficient calculations and simulation. As you've heard, real-time simulation is critical for the later portions of the development process, and Sim Driveline has specialized technology for that. There are clutches, gears, and transmission libraries. Again, it is hardware in the loop capable and can be combined with other tools to model the multi-domain system. For those of you who have not used the tool, we'll give you a brief demonstration so you can see how that works. So here we have a very simple vehicle model with an engine, a transmission, a controller, as well as longitudinal vehicle model and a tire model. If we look into this system, we can see the transmission itself, where we have a number of planetary gears that are combined with clutches. Depending on which clutches are closed, we'll determine which gear we're in and what the gear reduction is from the engine to the vehicle. In addition, we also have a vehicle controller, which has been modeled in Stateflow. So you can see in this very simple controller, depending on which gear we're in, signals are outputted to determine whether the clutches should be opened or closed. So if we run this simulation, you'll see how the vehicle accelerates from rest, goes through the different gears to reach its final speed. So to give you an impression as to how the physical modeling method works, in this drivetrain there's a component missing, or perhaps I have new technology that I wish to add. So I'm simply going to delete this mechanical connection, and I'm going to insert another component. The component in this case is a torque converter. I'm going to pull this directly from the Sim Driveline library and connect it using the mechanical connections that we described earlier. Once those connections are in place, we can re-simulate the model and see the effect that it has on the overall system. So I go down to the Simscape library, go into Sim Driveline. Here you can see some of the components that are available. For this model, I'll simply pull the torque converter out of the library and then establish the connection. As I mentioned before, these are physical connections that we're using, no longer using the input-output method. Now that this has been done, I can rerun the simulation and see what the effect on the overall system performance is, and we can see that the system functions much better now. To have done that in the input-output method would have required perhaps rederiving or re-implementing the other models and checking to make sure that the system-level equations were correct. Now, as the transmission engineer, I may need to determine which structure or which technology is going to be used in the final model. In this example, we have a 4-speed transmission. What I'm going to do now is replace that with a 7-speed transmission. So here's our 7-speed transmission. If I go back to my model, I can simply delete the 4-speed transmission with its controller, take this model from a library that I have prepared in advance, and connect it in. If we go into the transmission controller again, we can see we have a new transmission controller. It's very simple. It doesn't include the other features that we've talked about today that could take into effect other sensors in the system. And we can see that the transmission is now another step more complicated. We have additional clutches and additional planetary gears that have been brought in. I can rerun the simulation with this new transmission and new controller and see how it performs. And this is the type of test that I could be doing very early in the development process to see which architecture should I be using. In this case, it's simply a purely mechanical transmission, which you could also imagine as new electrical technologies come online or are available, that this could be integrated in the system as well. If we go back into the transmission model, we can see that the clutches that have been implemented or pulled from the Sim Driveline library also give us an indication as to the status of the clutch, if it's open or closed. And this is something that could be very valuable as I'm evaluating the performance of the transmission. There's other details that I could pull from the simulation, including the speed of the planets and so on and so forth, but this is the basic idea. I can connect these components together using these physical connections, do architectural level studies, and develop the control algorithm for this system. So this 7-speed transmission that you've seen here will then be integrated into the other portion of the solution in further demonstrations. So first, let me close down this model. And we'll go back to the presentation. And I will hand that back to Hagen so you can see the other portion of the solution.
Yeah, the other portion of the solution are the automotive simulation models, a ready-to-use simulation environment, which covers the whole powertrain and vehicle dynamics area. There are models available for different combustion engines in different levels of complexity, add-ons for simulating turbocharging, diesel exhaust, and so on. On the other hand, we have a vehicle dynamics model with add-on for truck and trailer simulation, for brake hydraulics simulation, and for surrounding traffic. And in the middle, between these two portions, we have the electric components, which cover electrical network components and detailed electric machine models. But as I said, the model are just one part. The other part is the usability, the access to the models. And for this, GUI is developed. We call it Model Desk and Motion Desk for parameter handling and for simulation observation. The models itself have all the same structure. They are developed in Simulink because we think that Simulink is a kind of standard in controller development. They are open, they are accessible down to the lowest level, and we have 5 main components. Each model has 5 main components: the engine, the drivetrain, the vehicle dynamics, and the environment. And this structure ensures that these models can be easily combined to complex virtual vehicles. And for the usability, we implemented a structured signal access kind of modeling guideline and a parameterization concept. Yeah, Model Desk is the GUI, as I said. It is developed for parameterization. The models, it has a part for road generation, for maneuver definition. The project management can be handled to create vehicle parameter sets, and you can also define vehicle model variants. And of course, it can handle the offline simulation models in Simulink and also the real-time simulation models on a real-time platform. Finally, a custom component parameterization, if you want to integrate your own models, is also possible. Yeah, now we combine these two things together. First, let me start with the initial model. We have chosen the one gasoline engine model, which includes a mean value approach of a engine simulation, which is included here. You can see the 5 main components again. Today we want to focus on the drivetrain because we want to integrate this 7-speed sim driveline model into this environment. Our drivetrain includes all the standard parts: crankshaft, transmission, differential, starter, and a dyno test bench for running driving cycles. And here in the vehicle dynamics, there's a very simple model for driving resistances to test the engine. When we now go into the detail of the transmission, for instance, we can see different components, and when you go down to the lowest level, you can see how it is implemented. And this is very important for a ready-to-use model. As a user, you have to know what is implemented in the model. You have to understand it, and you have to be flexible when you want to add to change it. Yeah, when we go from the model to the parameterization tool, you see that for each of the components. Here, layouts are available, and within the layouts, the parameters can be set independently, and then it can be downloaded to the modeling environment or to the real-time hardware. Yeah, this is where we start, the starting point. Okay, now I switch to the modified model. You can see here again the 5 main components, but you also see here we do not have a standard signal connection anymore, but a physical connection. Because in this model we changed the drivetrain completely. We integrated this 7-speed transmission example from the Sim driveline library. The starter and the test bench still remain. It is very easy to integrate it here. And also on the vehicle dynamics part, we integrated these longitudinal vehicle dynamics and the tire model from the Sim driveline library. And these blocks, these, let's say, custom-specific blocks, can now be integrated in the user GUI by registering a specific library. This specific library contains these blocks. And if I now open the belonging project, then I can see when I go into the parameter set, I do not have the transmission anymore here in the drivetrain basic, in the standard drivetrain, but I have a custom component. And within this custom component, I have this 7-speed transmission here. And for the 7-speed transmission, I have all the parameters available. For each of the clutches which are in the model, I can have access to the parameters. And of course, I can also these parameters modify and download. And when I now start the simulation, I can observe the driver behavior here. Let me stop this now here. I can have access to all the parameters in the model itself. I can observe the simulation results here. This is the speed, this is the gear, but I also have access to the internal variables of the model. For instance, here the clutch states, or the transmission speeds inside the transmission. Yeah, so you see it's very easy to combine the advantages of both worlds, to say, to a complete simulation environment with ready-to-use parts which come from a third-party supplier, and with specific models developed for specific tasks with the physical modeling method. Yeah, and then I give back to Steve. Shift F.
Okay, so hopefully you've seen that the power of combining custom off-the-shelf models with physical modeling solutions. It gives engineers the ability to set up new drivetrain variants without the pain of deriving and programming the system-level equations. We've seen how we can efficiently configure parameters in experiments, and these models that we've developed and used in the early phases of development can be used to test the controller through hardware in the loop. The specific example we've shown you how to do this combines Sim driveline and dSPACE, ASM, and Model Desk to get these capabilities. And the combination that we've shown you makes it easy for engineers to design efficiently, sharing models with one another, and use model-based design to use the same models from the start of the development process all the way through to the end. So thank you very much for your attention.